and good morning to all of you. I will be speaking in a concise and more applied manner how we will be going to check a sample that is handed me by Rakhi ji. Is all these samples are suitable for the production from the point of view of production of LC3. So what is the next step? Once you are handed over with the samples that is from the site that is sent by the geologist, what is the next step that you will be doing in your laboratory? So here I will be speaking about the techniques that you can use for the identification or qualifying whether a particular clay is suitable for the production of LC3 or not. And all these techniques you will be able to explore in this particular workshop during our practical session 2. So I will be speaking on what is clay in a generalized manner and why characterization is required, then how the quantification or identification of a particular material will be done from the LC3 production point of view. So as earlier Dr. Rashmi told that clay is very generalized term. All of us know that clay we have got in our life. That here I have presented two images. One is for the earthen pot and another one is for the modeling clay that we use in our school for modeling toys. What is the common in these two? These are plastic. What of these are plastic? So something which is plastic is called clay. The another one is particle size. The clay mineral have a finest particle size among the all available minerals. It has a particle size of order 0.2 micron. So okay, physically now we know something that is plastic and have a fine grain size. It is clay. Okay, let's have a look into its chemical composition. As we know, nature produces rarely anything in its pure form. The same is true for the clay. There are numerous minerals are listed in literature. As you will be going, the clay mineral, there are numerous minerals. But what is this common term? That is, they are collectively being called as clay. Okay, these are composed of aluminosilicate. Okay, now we know something that is plastic have a grain size of order 0.2 micron and composed of aluminosilicate. Now, the next thing is the layer structure or crystal structure. Based on the crystal structure of this aluminosilicate, we can again classify these minerals and broadly in three categories. So there is 1:1 type, 2:1 type, and 2:1:1 type. So from LC3 production, what we will be looking this 1:1 type clay, which is kaolin. Okay. Now we are in a position to state we will be looking at plastic material having a grain size of 0.2 micron, composed of aluminosilicate and a layer structure of 1:1. So we will be looking for the kaolin material. Okay. For identification and quantification of kaolin, we use four techniques. One is LOI, loss on ignition. Second one is TGA, DTG or DSC. Third one is XRF and the fourth one is XRD. The two, LOI and TGA, is based on the interaction of matter with heat. So we will be heating the material and we will be noticing what is happening with its weight. The second two, we will be interacting the material with X-rays and we will be noticing what is happening there. The initial three techniques, LOI, TGA and DSC and XRF, are based on this chemical composition, which is aluminosilicate. While the fourth one, the XRD, is based on its crystal structure, that be 1:1. Okay, now we will be going one by one in these four techniques. Okay. The first three techniques are based on its chemical composition. Let's have a look in its chemical composition. Kaolin is mineral composed of kaolinite, dikite, nekrite, and halloxides. Its chemical formula is Al2Si2O5.all4. Here I have displayed the molecular structure of kaolinite. As we can say, it contains 2 mole of crystalline water. So by using this information, we will be able to quantify and identify this kaolin mineral. Now here the calculation are presented as molecular formula is Al2Si2O5.5. Its molecular weight is 258.16 gram. So if we will be having a 39.50% alumina and 100% kaolin compound and a 13.96% of H2O. So by knowing the percentage of this alumina and the mass loss, we will be able to calculate the upper limit of kaolinite in particular sample. So after getting the sample, the first thing is the sample preparation. The first thing is the drying and a proper homogenization. As Dr. Rashmi told that there are mixed layer are available in mining sites. So first thing is homogenization and drying, followed by the crushing and milling and passing through a 45 micron sieve after milling it. So what is the particular requirement for the sample preparation? The sample must be properly homogenized. It should be dried below 50 degrees centigrade, and after passing it through 45 micron sieve, we must put into airtight container. So the first thing, the LOI and TGA techniques. Here we will be hitting this sample and we will be noticing the weight loss. The first is LOI, loss on ignition. We can get this loss on ignition by using a simple muffle furnace available in our laboratory. So by calculating this mass loss, we will be able to know this kaolin content. We will be particularly looking for the weight loss that occur between 400 to 600 degrees centigrade. As in earlier chemical composition slide, we discussed that 1% mass loss will be contributing to 7.17% of kaolin content. So we will be multiplying this mass loss with 7.17% and we will be able to get the maximum or the upper limit of the kaolin in respective sample. This is a PGA graph of a kaolin clay. Here you will be able to see why we will particularly concerned about the mass loss that appear between the 400 and 600 degrees centigrade. As we can see, the mass loss due to this crystalline water available in kaolin loses between 400 to 600 degrees centigrade. That's why we are concerned about the mass loss between 400 to 600 degrees centigrade while doing the LOE calculation using the muffle furnace. So here again we will be able to know the mass loss that occur between 400 to 600 degrees centigrade, roughly 400 to 600 degrees centigrade, and after multiplying it with 7.17, again we will be able to know the upper limit or the exact limit of the kaolinite content. The next two techniques are based on the interaction with X-rays. The X-rays are produced by the interaction of high energy electron with a heavy metal. Their energy ranges between 10 to 0.1 nanometer. Now the principle. The first technique is XRF. XRF technique, what is this? When a particular material is interacted with X-rays, it makes an electron ejected out from its inner orbital. As soon as electron ejected out from its inner orbital, an electron from next orbital heavy energy will occupy that space. So as there is an energy difference, this energy will be emitted as a secondary X-rays. So by quantifying and identifying these X-ray, we will be able to quantify and identify that particular atom. So X-ray is particularly speak about atom. It doesn't concern about its chemical environment. You may have CaCO3, CaO and CaCl2, but all of these will be showing the same signal because we will be looking for calcium atom. So how we use this technique in our lab? First is sample preparation. So the grounded sample is mixed with binder. In our laboratory, we generally use a boric acid. You may use some other. There are some glycolic material also used. Followed by the preparation of the pellet by using hydraulic pressure. This XRF pellet will be placed in X-ray machine, which will provide us the elemental composition of the sample. Here I have displayed the exact composition of a kaolin clay sample. Here the alloy is mentioned. This alloy is weight loss that appears at 1,000. Okay. Now in this slide, this is a particular importance. Now here I have mentioned the criteria by using which we will be able to whether a clay is suitable for the production of LC3 or not. The first one is the content of alumina. If content of alumina is above 15.8, then the clay is suitable. If alumina by silica ratio is above 0.2, okay, this clay is suitable. Alloy must be greater than 5.6. So here I have displayed the chemical composition alloy of two clay sample, clay A and clay B. For clay A, the alumina content is 26.05, which is greater than 15.8. 15.8. Okay, it is qualifying the first criteria. The second criteria is alumina by silica ratio. For clay A, this is 4.7. It is qualifying this criteria too. For the alloy, the criteria is 5.6. For clay A, it is 9.39. So it is clay A is suitable and it is qualifying the criteria. So it is passed the quality check for the production of LC3. While we will be looking at clay B, which is having a lower alumina content, lower alumina by silica ratio, and followed by the lower alloy. So we will not proceed with clay B further. So here the selection criteria that will be used for qualification of a particular clay, the alloy, TGA and XRF base. Now the last one is the XRD. XRD was concerned about more about the structure. So what is structure, as Rashmi told already? It is a 1:1 clay having a tetrahedral sheet and an octahedral sheet. Its structure is triclinic. So what is the principle of XRD? It works on the principle of Black's law. It states n lambda is 2d sin theta. In laboratory, how we use this XRD? The finely grounded sample is subjected to X-ray XRD characterization, and here is a typical XRD graph. Here we can see if we are having a peak at 12, it is a sign of happiness for us. Okay, it is a clay material. Now we can also quantify this kaolin by Rietveld analysis, that is XRD based quantification. And here I have mentioned some of the phases that we can add to the Rietveld analysis while quantifying the phases by phases using XRD. Thank you.